Ever think about those invisible forces making our gadgets, instantly responsive? Like from the tiniest smart sensor picking up a temperature change, maybe, to a big industrial robot reacting to an error. How do they do that? React in real time without just checking constantly. Well, today we're diving deep into exactly that: interrupt handling in embedded systems. Our mission, really, is to unpack this pretty foundational concept, make it clear why it's kind of a hidden superpower in almost all the tech you use.
It absolutely is. At its core, interrupt handling is it's what lets the CPU, the brain of the device, react super quickly and efficiently to things that happen, well, unpredictably. Asynchronous events, we call them.
Hmm.
Think of it as the ultimate way for hardware and software to talk instantly, making sure time-sensitive stuff gets dealt with right away.
Right. And to really get how big a deal that is, maybe we should look at what came before, this thing called polling. It's like, imagine a kid in the backseat just constantly asking, are we there yet? Are we there yet?
Exactly. The CPU just checks every device again and again and again. Is there anything new? Anything?
Yeah, you can just picture the CPU getting totally bogged down, right? Huge overhead and delays responding to anything actually important.
Precisely. And that's why interrupts are such a profound shift. Instead of that constant checking, interrupts are event-driven.
Hmm.
The CPU can basically chill out, maybe go into a low power mode until something actually happens.
Ah, okay, so it's like getting a notification when you arrive, not every 5 seconds on the way.
You got it. And that just slashes the CPU overhead, makes
Yeah.
responses immediate when they need to be.
So the difference is huge then. You get like three big wins. First, efficiency, right? The CPU isn't constantly busy.
Much lower utilization, yeah.
Then responsiveness, super quick, direct reaction, no polling delays.
High and immediate, definitely.
And this third one is massive, especially for, everything battery power, power consumption. It drops significantly.
Hugely. The CPU can sleep. That's critical for phones, wearables, IoT stuff. Lets them last days, not minutes.
So, next time your phone screen lights up instantly or your smart doorbell pings, remember there's this fundamental engineering choice behind it, making things fast, reliable, and not draining the battery.
Okay, let's really get into the aha moment then. How does this invisible magic actually work? Picture the CPU, it's busy running code, and then bam, something urgent pops up. How does it just stop, handle it, and then pick up exactly where it left off? Like nothing happened.
Okay, so it all kicks off with the event occurrence, the trigger. This could be something external, maybe you press a button or data comes in from a sensor over, say,
Internal.
yeah, or internal, like a timer inside the chip finishing its count, or a DMA transfer completing that's direct memory access, or maybe even an error like the CPU trying to divide by zero. Something went wrong.
Okay, event happens. Then what?
Then a dedicated piece of hardware, the interrupt controller, spots it. You can think of it like a super efficient receptionist. It sees the event, figures out its priority compared to anything else waiting, and signals the CPU, hey, something needs attention.
Got it. So the CPU gets the signal. Right. First, it finishes whatever tiny instruction it's currently doing.
Okay.
It doesn't just stop mid-thought. Then it does this crucial thing called a context switch. It basically saves its current situation.
It saves its state. What does that mean exactly?
Yeah, its state. Onto the system stack, which is a special area of memory.
Yeah.
And that state includes, well, everything important. Where it was in the program counter, or PC, its current operating status, the status register, and the data it was working with in its general purpose registers.
And saving all that takes time, right?
It does. But here's the amazing part. In a lot of modern chips, like the ARM Cortex-M series, this whole saving process, this stacking, is automated entirely in hardware.
Oh, wow. Hardware does it all.
Completely. Pushes specific registers onto the stack automatically. And because hardware does it, it's incredibly fast, has a fixed minimal overhead, and crucially, it's predictable. The timing is consistent. It's absolutely vital for real-time systems where timing is everything.
State saved. Now what? It needs to know what to do for this specific interrupt.
Exactly. So now it consults the interrupt vector table, the IVT. Think of it like a directory or lookup table. It's predefined, usually stored in memory, and it tells the CPU the exact address for the correct interrupt service routine, or ISR, for that specific event.
ISR, the handler code.
Right. The CPU jumps to that address and starts running the ISR code. That's the code written specifically to handle that button press or that incoming data or whatever triggered the interrupt.
And these ISRs, are they big, complex pieces of code?
Ah, good question. No, quite the opposite. There's a really crucial design rule here. ISRs should be short and do minimal work. Their main job is often just to quickly clear the interrupt source, maybe grab some essential data like read a sensor value,
Yeah.
and then often they'll just set a flag or put some data in a queue to signal the main program, or maybe trigger a task in an RTOS, a real-time operating system. Let the main code handle the heavy processing later. We sometimes call it the ISR's coordinator pattern. Keep the ISR super fast.
Makes sense. Get in, do the absolute minimum, get out. But you mentioned clearing the source.
Yes, absolutely critical. Interrupt acknowledgement. Inside the ISR, you must clear the flag that indicates this specific interrupt happened.
Why is that so vital?
If you don't, the moment the ISR finishes and the CPU goes back to normal, the interrupt controller will see the flag is still active and signal the CPU again, immediately.
So you'd get stuck in an endless loop just running the same ISR over and over.
Exactly. Instant system crash, pretty much. So clearing the flag is non-negotiable.
Okay, so ISR runs, clears its flag, then what? How does it get back?
So once the ISR finishes its short task, the CTU performs context restoration. It pulls all that saved state that registers the program counter back off the stack. Control then returns to the exact instruction in the original program where it was interrupted.
Wow, so the main program just picks up right where it left off, totally unaware it was paused.
Precisely. As if nothing ever happened.
That whole process, pause, save state, jump to handler, run handler, clear flag, restore state, resume. It sounds complex, but it must happen incredibly fast.
Milliseconds, microseconds, even nanoseconds, depending on the system.
And that seamless juggling act, that's what lets our devices handle hundreds of things at once, prioritize what's critical, all without us noticing the complexity underneath. It really is the unsung hero.
Absolutely.
Okay, that flow makes sense, but let's talk about the key players, the components making this happen. We mentioned ISRs.
Right, the interrupt service routines. Specialized software, like mini programs laser-focused on handling one specific type of event, designed to be quick, non-blocking, minimal.
And the interrupt controllers, you called them the traffic cops. Tell me more about how they've evolved.
Oh, they've come a long way. Early ones, basic PICs, programmable interrupt controllers, they were simpler. They'd tell the CPU an interrupt happened, but the CPU might still have to poke around, do some software checks to figure out which device actually sent it. That added latency.
Not ideal for real-time stuff.
Not at all. Then came things like the Vectored Interrupt Controller, or VIC, especially in ARM processors. That was a big step. Hardware figured out the source and directly provided the ISR address to the CPU. Much faster.
Okay, getting smarter.
Definitely. And now, in modern systems like those using ARM Cortex-M cores, you have the NVIC, the Nested Vectored Interrupt Controller. This thing is tightly integrated right with the processor core. We're talking extremely low latency.
What makes it so powerful?
Well, it handles prioritizing interrupts with lots of configurable levels. It allows higher priority interrupts to interrupt lower ones that's nesting. It even handles the processor state saving and restoring automatically in hardware, like we discussed.
So the trend is clearly moving complexity out of software and into dedicated hardware.
Exactly. Offloading that time-critical management to hardware. It makes systems faster, more predictable, and actually simplifies the software developer's job in some ways. Allows for handling way more simultaneous events than you could reliably manage purely in software.
Fascinating evolution. And the third key piece you mentioned was the interrupt vector table, the IVT, the system's phone book.
Yeah, or like a dispatch table. It's this critical data structure, usually in non-volatile memory like flash. Each entry points directly to the starting address of a specific ISR. When interrupt number 5 happens, the CPU looks at the 5th entry in the table, finds the address, and jumps there.
And its stability is crucial, you said.
Absolutely paramount. Because it's usually fixed or managed very carefully, it provides determinism. If that table gets corrupted or points to the wrong place, well, the system could jump anywhere. Crash, unpredictable behavior, maybe even security holes if it jumps to malicious code.
Yeah.
It's really the system's hardwired response plan.
So these three, the quick ISRs, the smart hardware controllers like NVIC, and the stable IVT, they all work together, like that highly trained pit crew analogy.
Precisely. Ensuring predictable, reliable responses even when things get hectic. That's the core machinery.
Makes sense. So if that's the machinery, what about the signals themselves? You mentioned different types of interrupts. What are they and why does it matter?
Right, we categorize them based on where they come from and how they act. The big split is hardware versus software interrupts. Hardware ones are triggered by physical events, button presses, sensor data, timer expiring. They're asynchronous. They can happen anytime, totally unrelated to the code being run.
Okay, real-world events and software interrupts.
Those are deliberate, triggered by software instructions, things like system calls, where your program needs the operating system to do something, or maybe for debugging breakpoints. They happen at a predictable point in the code execution.
Got it. Hardware is asynchronous, software is synchronous. What else?
We also talk about external versus internal interrupts. Often, internal ones are called exceptions. External ones come from outside the CPU chip itself. I/O devices, keyboards, network interfaces. They let the system react to its environment.
And internal ones, or exceptions?
They're caused by something inside the CPU or memory system going wrong. Usually program errors, trying to divide by zero, accessing invalid memory, running an illegal instruction. The CPU itself flags an error condition. In ARM Cortex-M, these are often system exceptions.
Okay, internal errors versus external events. What about disabling them? Can you just turn interrupts off?
That brings us to maskable versus non-maskable interrupts, or NMIs. Most standard hardware interrupts are maskable. That means software can temporarily disable or mask them. You might do this briefly to protect a really critical piece of code that absolutely cannot be interrupted.
Like when you're updating shared data.
Exactly. You disable interrupts, update the data, then re-enable them. It's common. But you keep that disabled period extremely short.
And non-maskable, the NMIs.
Those are the big red emergency buttons. They cannot be disabled by software, no matter what. They're reserved for the most critical, potentially catastrophic events where the system must react immediately. Think power failure is about to happen, or a system watchdog timer expiring because the software seems to have crashed. Any delay could be disastrous.
So NMIs are for true emergencies only.
Absolutely. Highest priority, unstoppable.
One more distinction, how the signal itself is detected.
Right. Edge-triggered versus level-triggered. Edge-triggered means the interrupt fires on a change, a transition, like when a signal goes from low to high, rising edge, or high to low, falling edge. Good for discrete events like a single button click or a pulse from a motor encoder.
And level triggered.
That means the interrupt is active as long as the signal stays at a specific level, either high or low. It's more for conditions that persist, like maybe a sensor indicating an overheat condition stays high until the temperature drops.
So edge for momentary events, level for ongoing conditions.
Generally, yeah. And engineers really have to think about these distinctions. Choosing the right type, setting the right priorities, deciding what's maskable. It all feeds into making the system not just fast, but robust and safe, especially in things like medical devices or cars. Designing for all contingencies.
It sounds like managing all this, especially in a complex system with potentially hundreds of interrupt sources, could get pretty tricky. What are the more advanced strategies engineers use?
Yeah, it definitely requires careful management. Prioritization is key, as we touched on. You assign priority levels. Simple systems might use fixed priority interrupt. A always beats interrupt B. More complex ones might use dynamic priority, where the urgency can change based on what the system is doing.
And you mentioned preemption.
Right. That's where a higher priority interrupt can actually interrupt the ISR of a lower priority one that's already running. Ensures the most critical things get handled fastest. In ARM Cortex-M, you can even divide priority into preempt priority and sub-priority for finer control. Lower number usually means higher priority.
And nesting, that's related, right?
Nesting is when preemption happens. An ISR gets interrupted by a higher priority ISR. It allows incredible responsiveness for top priority events. But you have to be careful. Too much nesting could potentially lead to stack overflow if you keep saving context repeatedly, or tricky situations like priority inversion.
Priority inversion, what's that?
That's a classic problem, especially with operating systems. Imagine a low-priority task holds a resource, like a data lock, that a high-priority task needs. The high-priority task gets blocked, waiting for the low-priority one. Then, a medium-priority task comes along and preempts the low-priority one. Now your high-priority task is stuck, waiting for both the medium and low tasks to finish. It's inverted the priorities. Need careful design to avoid.
Okay, tricky stuff. What about masking? Any advanced techniques there?
Yeah, beyond just turning all interrupts on or off globally, some architectures give you finer control, like priority-based masking. For example, in ARM Cortex-M, you can set a register called base pry. This tells the processor to ignore any interrupts below a certain priority level, but still allow higher priority ones through. More granular than just a global on-off switch.
And the hardware itself helps manage this complexity. You mentioned optimizations?
Oh yeah, modern controllers like the NVIC are packed with them. One really cool one is tail chaining. Imagine you finish an ISR and another interrupt is already waiting. Instead of fully restoring the old context just to immediately save it again for the new interrupt, tail chaining skips that. The hardware just loads the next ISR's info and jumps straight to it.
Cuts out the middleman, saves time and power.
A significant amount, especially if you get bursted interrupts. It dramatically reduces latency.
Any others?
Another clever one is late arrival handling. What if a really high-priority interrupt arrives just as the processor is starting to save state for a lower priority one? Or maybe just as it's finishing restoring state? The NVSE is smart enough to recognize this, quickly abandon the current save restore if needed, and immediately service the late-arriving high-priority interrupt with minimal delay. It's all about minimizing latency for the critical stuff.
It's amazing how much intelligence is built into the hardware now, but it does raise that question, doesn't it? How do engineers balance trying to get the absolute lowest latency with keeping the system predictable and flexible? These advanced features sound powerful, but maybe complex to use perfectly.
That's the core challenge. These features require a deep understanding to leverage properly for a specific application. It's always a trade-off.
Which probably leads us nicely into designing the ISRs themselves. If they're at the heart of the response, how do you make sure they're robust and efficient? Are there golden rules?
Absolutely. This is really where the rubber meets the road. Rule number 1, we've hinted at it. Keep ISRs short and concise, minimal processing. Acknowledge the interrupt, maybe set a flag or grab essential data, then get out. Minimize time spent in interrupt context.
Okay, keep it brief. Rule 2.
Avoid blocking calls.
Yeah.
Critically important. Never, ever put things like software delays, delay functions, loops that just wait for something, busy waiting, or I/O operations that block inside an ISR.
Why is that so bad?
Because if your ISR waits, nothing else can happen at that interrupt level or lower. Other interrupts might be missed entirely. The whole system can become sluggish or even seem frozen. ISRs must be non-blocking.
Right. So rule 3 must be about handling the work that takes time.
Exactly. Defer non-critical processing. If an interrupt means you need to do some complex calculation or send a big chunk of data, don't do it in the ISR. Instead, have the ISR maybe put the raw data into a buffer or queue or set a flag. Then let your main program loop or a dedicated task in an RTOS pick it up and do the heavy lifting later, outside the interrupt context. That ISR's coordinator idea again.
Okay, defer the big stuff. What about data sharing? If the ISR updates data the main code uses.
Rule 4. Ensure data integrity for shared data. This is subtle but crucial. If an ISR modifies a variable that the main code also reads or modifies, you need to protect that access. Imagine the main code is halfway through updating a multi-byte value and an interrupt comes in and modifies the same value. You could end up with corrupted data.
So how do you protect it?
Operations on shared data need to be atomic. They must complete entirely without being interrupted. Sometimes this means briefly disabling interrupts around the access point. These are called critical sections.
But you said keep interrupts enabled as much as possible.
You do. So these critical sections must be as short as absolutely possible. Just protect the access itself, then re-enable interrupts immediately. Disabling interrupts increases latency for everything else. Also, related to this, functions called from an ISR should ideally be reentrant. That means they can be interrupted and called again safely, usually because they only use local variables, not shared global ones. Prevents weird interactions.
Okay, atomicity and reentrancy. What's next?
Rule 5. Manage interrupt flags meticulously. We mentioned this, but it bears repeating. Always, always explicitly clear the interrupt source flag within the ISR. Forget this, and you get infinite loops.
Got it. Clear the flag. Last rule.
Rule 6. Leverage hardware features. Don't make the CPU do work that dedicated hardware can handle better.
Right.
A prime example is direct memory access, DMA. If an interrupt signals that data needs to be moved, say from a sensor peripheral to memory, use DMA. The ISR just tells the DMA controller, move this much data from here to there, and then the ISR can finish. The DMA hardware handles the actual byte-by-byte transfer in the background without bothering the CPU. Hugely efficient.
So use the tools the hardware gives you.
Definitely. It frees up the CPU and keeps ISR short.
It really highlights that constant tension, doesn't it? Trying to be incredibly responsive while also making sure everything stays consistent and correct. Lots of trade-offs.
It's the art and science of embedded systems design, really.
Okay, we've covered the how, the who, the types, the rules, but let's get real. What are the big challenges? What keeps engineers up at night when dealing with interrupts? And how do you even debug these things when they go wrong?
The challenges. Yeah, debugging is definitely high on the list. But maybe start with 2 performance killers. Interrupt latency and jitter. Latency, as we said, is the delay from the interrupt signal to the ISR starting. Too high, and you miss real-time deadlines. Simple as that.
And jitter.
Jitter is the variation in that latency. Maybe one time the latency is 10 microseconds, the next time it's 50. That unpredictability, that jitter, can be just as bad or even worse than high latency in many systems. Think audio streaming or precise motor control. Jitter causes glitches, instability.
So you need low latency and low jitter. Consistent timing.
Exactly. The system's total response time depends on that latency, plus how long the ISR runs, plus the context switch time. It all adds up.
And debugging this sounds like a nightmare. Why is it so hard?
It's what some call an observability challenge. The core problems are the asynchronous nature and the non-determinism. Interrupts can happen literally between any two machine instructions. This makes race conditions where the outcome depends on the unpredictable timing of events really hard to reproduce. And traditional debugging, like setting a breakpoint and stepping through code,
Yeah. What's on that?
it changes the timing. Halting the processor completely alters the sequence of events. The bug you're hunting might simply disappear when you're debugging, only to reappear when the system runs at full speed. It's incredibly frustrating. You're chasing ghosts.
So you need special tools, a detective's kit.
Pretty much. Hardware debuggers are essential. Tools that connect via JTAG or SWD interfaces. They let you see what the processor is doing, examine memory, and set hardware breakpoints, which can stop the CPU based on specific conditions without intruding too much on the timing.
Okay, less intrusive debugging. What else?
Trace analyzers are incredibly powerful. They capture a log, a trace of the processor's execution path over time. Which instructions ran, which functions were called, when interrupts occurred. You can analyze this trace offline to reconstruct exactly what happened and pinpoint timing issues or unexpected interactions.
Like a flight recorder for the CPU?
Kind of, yeah. And if you're using an RTOS, then RTOS-aware debuggers are invaluable. They understand the operating system's concepts, tasks, queues, semaphores. They can show you task states, context switches, help you find issues like that priority inversion we talked about, or deadlocks.
So specialized tools are key. Anything else in the toolkit?
Well, good old-fashioned logging can help, if done carefully so it doesn't impact timing too much. Profiling tools to measure ISR execution times. And just really careful analysis, maybe using hardware breakpoints strategically.
And testing must be rigorous.
Oh, absolutely essential. Unit testing individual ISRs in isolation. Integration testing to see how they interact with the rest of the system. System testing under realistic loads. And importantly, stress testing hitting the system with high rates of interrupts and maybe even fault injection, deliberately causing errors to see how the system recovers. Plus, things like code reviews and static analysis tools can catch potential problems before they even get to hardware.
It sounds like debugging RTOS-based systems adds another layer, too.
It does. The RTOS simplifies managing tasks, but it adds abstraction. Debugging often involves understanding the RTOS's internal state. And sometimes you might need to use specific RTOS API calls within your ISRs that are designed to be interrupt safe, which might slightly increase latency but guarantee system stability. It's another trade-off.
Wow. Yeah, the whole debugging side really drives home that embedded engineering isn't just about writing code that works sometimes. It's about meticulous detection, prevention, making sure these invisible processes are reliable always.
It's a continuous challenge for sure.
So wrapping this up, we've gone deep into interrupt handling. And hopefully it's much clearer now that this isn't just some obscure technical detail. It's truly fundamental. It's the engine enabling efficient, real-time responses in basically everything, massively outperforming that old polling method in CPU use and, critically, power saving.
Absolutely. And looking forward, the trends seem pretty clear. We'll likely see even more hardware acceleration for interrupt management. Controllers getting even smarter, latencies dropping further. Power management will get even more tightly integrated with interrupt handling, trying to squeeze every last bit of battery life out of devices by allowing deeper sleep states.
And the debugging headache.
Well, the challenges aren't going away, especially with multi-core systems and complex RTOS interactions. So we'll definitely see continued innovation in non-intrusive trace and analysis tools, making that detective work more manageable. And one more thing. As we push more AI and machine learning to the edge, onto these embedded devices themselves, interrupt handling will need to adapt again. Maybe we'll see more intelligent, adaptive interrupt controllers that can manage these new, often unpredictable, asynchronous data flows from AI models or complex sensor fusion. It's an exciting area.
Definitely sounds like it. So maybe a final thought for you, the listener. Next time you use any smart device, your fitness tracker, your phone, maybe even your car's infotainment system, just pause for a second. Think about that seamless interaction, that feeling of instant response, of reliability. How much of that is really a testament to this invisible symphony, this constant high-speed dance of interrupts orchestrating your digital world behind the scenes? And maybe ask yourself, what new possibilities open up as these systems get even faster, even smarter, even more aware?